So here's an example of an optimization problem that's going to contain an open interval. So this is on the PDF sheet that's attached. It's the problem to do with the container. So your goal is to build a box that has an open top with a certain volume. So I always like to joke around with my students, like let's say you have a pet turtle and you love your turtle so much. And you and your turtle have decided that you're going to build it a special home. And you want your turtle to live, so it's got to be a box and it's got to be an open box. And so you're going to build a base here for your turtle, and then you're going to have these beautiful clear plexiglass sides so that your turtle can breathe, and it's wonderful. You feel great about this. So you've decided that, all right, this is the box that I'm going to build. And it has an open top, and it has to have a volume of 10 cubic meters. Man, you love your turtle. That's a big box. Okay, so now that you've got everything sorted out, you realize that as you're on your way to the Home Depot to buy the material, you're costing it out. So the material on the sides is a certain price, $6 a square meter for the plexiglass, and the material on the base is more, you want to put like marble or something on the base. You love your turtle. So you do love your turtle, but you want to build this box as cheaply as you possibly can, right? You don't want to spend thousands of dollars. You would like to make it as cheap as you possibly can. So in this problem, we're going to try to optimize or minimize the cost. So that means that eventually we need to come up with some function for the cost. Now, this seems a bit daunting when you try to dive right into it, so I'm going to follow the procedure. I've got an open-topped box, kind of like this. There's some different material on the sides than there is on the base. Now, as I read through this problem, there are a lot of key words that pop up: volume, cost, and cost per square meter, so area. So I think it's sensible that I'm going to try to connect them. Let's say that V is the volume of the box in cubic meters. Let's say that H is the height of the box in meters. Now, on my picture, as soon as I define my variable, I will put in that variable just so that I can visualize it. I'll say that W is the width of the box. And so let's say that this is W, and we'll say L is the length of the box. And we'll say that. Now, in every problem that we solve, we need to find a max or min of a certain quantity. That has to be made clear to you. You really need to understand what it is you're trying to optimize. So in our case, we are going to say that C is the cost of the box. That's what we are trying to find. We want this. So I now need to come up with a function that is going to model C. And that's the thing that I eventually want to differentiate. Okay, so now comes step 3, the function. How do you start? Things like balancing units are important, but we're going to break it down based on the information that we've got. We have been told a lot about cost per area. So cost for the material on the sides of the box, that kind of thing. Okay? So the cost in total is going to be the cost for the material on the sides plus the cost for the material in the base. The cost for the sides or the base is calculated in the same way. It's going to be a cost per area on the sides times the area of the sides. And so this would be in dollars per square meter. This would be in square meters. You could see that the units will balance out there. This is going to be the cost per area of the base times the area of the base. Now again, dollars per square meter multiplied with square meters. Those are going to go away and we'll end up with the proper units. So we'll say that the cost is represented by C, And now we're going to start filling this in. I know that the cost per area for the material on the sides is $6 a square meter. And now I need to talk about the area of the sides. Well, there are two different sides. If I scroll up here, this will be considered one of the sides. And so will this. And they come in pairs. So we'll have the front and the back walls. So the sides in this particular case, there are two of each flavor. Each one of them is going to have a height and some sort of dimension here. So if I go down and I talk about the area of the sides, I'm going to have two bunches of L times H and two bunches of W times H. And again, if we scroll up, we can see that there's an L times an H here. And there's a W times an H over here. And there are two of them for each side of the wall. Now, on the base, the cost per area of the base is slightly different. It's at $10 a square meter. And there's only one base. Its dimensions are length times width. So if I simplify this, here's what I'm going to find. There's a common factor of 2 that I can take out, so I'll have a 12. There's another common factor of H that I can take out, so I'll remove that. And then I'll have an L plus W times 10. L times W. So what I was mentioning earlier is that now we do have a function for the cost. This is the cost function, but it's a function of 3 variables: the length, the width, and the height of the box. Now that all makes sense, right? We should fully expect that the cost will depend on the size of each one of those faces. So this is a 3 variable function. What we have to do is we have to remove 2 of the variables somehow. And to do that, we have to use the given information. If you read through the statement of the problem, there are 2 critical pieces of information here. We are told, number 1, that the length of the box is to be twice the width of the box. So your turtle is really particular. It only wants to live in a box where the length is twice the width. Okay, fine. The other thing that we're told is that the volume of the box has to be 10 cubic meters. And the volume of any box is the length times the width times the height. So that means what we're going to do is put all of this information in. The most straightforward thing to do at the beginning is to substitute that expression for L. So we'll get a 2W plus a W in for there, 10 times 2W times another W. So we'll end up getting 3 W's from here. 3 times 12 is 36 WH plus 20 W squared. So what we've done is successfully reduced this function from a function of 1 variable to a function of 3 variables to a function of 2 variables. We have to keep going. And the other fact that we're going to use is this. So we have to make a little bit of a decision. So we'll have that 10 is equal to length times width times height. But because we know the length is twice the width, we end up with this relationship. So, what do? At this point, we have to make a decision. Should we get rid of the W squareds or the H's? Because this equation is given to us in terms of a W squared, and we have a single W in our cost function here, it probably ends up being a little bit easier to just solve for H. And so H is then going to be 5 over W squared, and we are going to substitute that in the expression above. So wherever we see this h, we are going to replace it with this. And so what we will end up getting is a function that has a single variable, just w. And when we put it in, we end up with something like this. 180 over w plus 20w squared. So this is cost as a function of the width. Now, if I really wanted to, I could have made it as cost as a function of length or cost as a function of height, but it just turned out that the details of this problem made my life a bit easier if I just studied it this way. So, now I've finally got my function. I've got the cost function ready, and I have to start attempting to differentiate it. I want to find the absolute minimum. How do I do it? You need to study the domain of this function so that you can have a plan of attack. The domain of this cost function, width is a positive number. Generally, it should be 0, greater than 0, or even equal to 0 at the very least. It's a physical dimension. You can't have a negative length in this particular problem. It's a physical constraint. Now, mathematically, if you look at the function that we've been given here, it doesn't have any problems except for one value. W can't be 0, and that's from the function itself. So that means that the domain of this function turns out to be an open interval, 0 to infinity. You can't be at 0, but you could conceivably have any width you want. Now, practically, you can't do that. You can't go to the Home Depot and buy a slab of marble that's 10,000 kilometers long. It's not possible. How are you going to fit it into your car? Because of this, we are going to use this modified first derivative test that I discussed earlier. And what that's going to entail is us now having to differentiate. So we are going to find c prime of w, which means that, okay, I've got my function, I know its domain, I'm going to differentiate the cost function. So it was 180 over w times 20w squared. So this is a really straightforward derivative for us to compute. Negative 180 over w squared plus 40w. Now, as always, I have been trying to get the message across to you that in order to make headway, in order to study this, we need to factor. We need to factor these functions and make them as simple and as neat as possible, because it will help us when we study the rest. So if I factor out a 20 and a w, I end up with a 2 subtract a 9 over w cubed. Now, I want to deal with this, sorry, not w cubed. I'm going to, my mistake. Here's what I should do. I'm just going to factor out a 20. And then I'll get a w, a 2w minus a 9 over w squared. That's the first step that I should do. Then I'm going to put everything over a w squared. That's going to make it a little bit clearer. So I apologize for goofing that one up, but this is the way that I want to go about it. All right. When it's written like this, it's a little bit easier to see what's going on. If that's the derivative, you could see that c prime of w does not exist when w is equal to 0, but this is technically not in the domain, so it's not a critical point. And then you can see that c prime equals 0 when 2w cubed minus 9 is 0, or w is the cube root of 9 over 2. And if you take your calculator and you crunch out W is the cube root of 9 over 2. It's somewhere in the ballpark of about 1.651. But that's not useful for us right now. That's a little bit later. So I'm going to build a sine table for C prime. My sine table technically is going to start here at 0. I'm going to have this one critical number, cube root of 9 over 2. My second derivative, I could combine these factors out front because their sign will always stay the same. Or my first derivative, sorry. This is always positive. It's irrelevant what's going on with the 20. This other factor will be negative until I cross that critical point, at which point afterward it will be positive. So you can think of a number like a billion. So the first derivative is negative going into positive. Now, according to what we had discussed before, since this is the only critical point, and we are then going from decrease to increase, this point here is an absolute minimum for the function c of w. If you wanted to, you could take a graph of this function and study what it looks like. And this could be for verification. You could take a look at the graph of c of w. It would look something like this. And the lowest point on this graph would happen right there on the w-axis when we're at the cube root of 9 over 2. But the question here is asking us for the value. What is the cost? When I go to Home Depot, I need a bunch of information. I need to tell the person that's working, I need this material. These are the dimensions I want to cut it at. And this is the ultimate cost that I should expect. So that means that the width will be about the cube root of 9 over 2. So that's about 1.65 meters. I know that the length has to be twice the width. So that's going to be about 3.3 meters. And then the height is 5 over w squared. We got that from the volume calculation earlier. And I think this turns out to be about 1.83 meters. This is huge. This is a big tank. You really love your turtle. Now, that's when I go to the store. So imagine a box that's about 5 feet wide by about 10 feet long and about 6 feet high. That's a huge box. How are you going to fit that in the SkyTrain or in the car? We won't worry about that right now. We'll just calculate the minimum cost. So what you do is you take the original cost function and you plug in the cube root of 9 over 2. So it'll be 180 over the cube root of 9 halves squared. Oh, sorry, not squared, just 1 over. Plus 20 times the cube root of 9 over 2 squared. And this one you can take a calculator and crunch it out however you'd like. It will turn out to be about $163.54. So the conclusion here, the minimum cost of the box is $163.54, and this will occur when the width is the cube root of 9 over 2, the length is twice that, and then the height is 5 over that width squared. So these problems are long, they're involved, there's a lot of steps, but following the procedure will help you understand how to attack each one of them. Again, all the problems will be different, but how you attack them is the same. You always have to end up with a one variable function for your situation, a model, differentiate it, and use the techniques we've talked about before.